Dear students, welcome to another lecture in statistical quality control. Today, let us see about the plotting of Xbar chart and R chart. Now, in plotting this, the first step is we have to calculate the arithmetic mean X bar or the average X bar and the range R for each sample. In each sample means it is like in each sample there may be a few few workpieces which whose dimensions are to be measured. In a sample means you can say F5 objects or 10 objects like that. Okay, so a good number of samples of items manufactured are collected randomly. Samples collected means each sample consists of 5. You take it as 5. Okay, each sample of 5 items that are manufactured and collected randomly. You have to collect randomly at different time intervals. You see, you should not start collect. You should not collect as soon as the machine is started in the morning, or when suddenly there is some fluctuation, some voltage fluctuation or something like that. It's some abnormal cases you should not collect. When the routine, when the flow is there, at that time you should collect. Okay, and their quality characteristics like diameter, thickness, length, weight, these are the quality characteristics. We'll say these are to be measured. Now for if you take diameter, for a diameter alone a control chart can be made, will be made. For thickness, if that is a quality characteristics, for that another chart will be made like that. Okay, for each quality characteristic one chart will be made. Okay, so now a good number means a sufficient number of samples. Sufficient number of samples means, see, one sample is consisting is 5 and such many number of samples. You can say, see, in each item 5 samples are there, and like that 10 samples we have taken. So how many objects we are going to measure? Around 50 objects. 50 objects we are going to measure, like that it is. Okay, so for example, if a sample consists of 5 items, now that is represented by the small letter n, small n, lowercase n. Okay, now what is lowercase n? It is 5, because we are having 5 items or 5 workpieces or 5 objects, whatever you call it. Okay, and these items dimensions x1, x2, x3, x4, x5 are measured. You see, you take for the time being that the dimension is diameter. Now the diameter d1, d2, d3, d4, d5, like that, Okay, the dimension can be anything, so we called it x1, x2, x3, x4, x5. 5 samples. Now if you want to calculate the average of this or the mean, arithmetic mean of this, see what is the arithmetic mean? Arithmetic mean X bar is given by x1 plus x2 plus x3 plus x4 plus x5 upon the total number of items, that is 5. So see, suppose 5 students are there and their average marks we want to calculate. So you add up all the marks of the 5 students and divide by 5. See, that's how you get the average. Now the same thing here, like that you calculate the average. And so X bar we calculated. Now next we have to calculate range. Now range is what? See, what is the largest value and what is the smallest value? Suppose in terms of marks, if you see, one student got 90 marks, another student got 50 marks, and the other 3 got in the middle somewhere between 90 and 50. Now what is the range? See, the range is from 90 to 50. That means what? 90 minus 50. That means the largest value minus the smallest value, 40. That is the range. You see, like that you have to calculate a range. You know, these things now we can calculate for each sample. Or you can say sample means subgroup. Okay, subgroup. If I am saying sample, no, there may be a little confusion in your mind. But if we say subgroup, no, it will be more clear, isn't it? Okay, each subgroup will have some 5 items, like that it is. Okay, now calculate X bar R in similar manner for the remaining number of samples. You see, for the first sample we have calculated. Okay, see, for the first sample calculated average and range are X1 bar and R1. Then remaining samples for the second sample it will be X2 bar, for the third sample X3 bar, for the fourth sample X4 bar, so on, Xn bar. Suppose if you are having 10 samples, then it will be X10 bar, like that. Similarly, the ranges will be first one is R1, the second one will be R2, R3, R4, so on to Rn. So if our number of samples is 10, it will be R10, like that. Now capital N, see, these are the number of samples. See, here there is a mistake here. I should have put it as capital N here and here. So there is a mistake, please correct it, because small n we are using for this, the sample size. Okay, whereas capital N we are using for number of samples collected. Okay, 1 minute then. Yes, it should be X2 bar, X3 bar, X4 bar, so on to Xn bar, and R1, R2, R3, R4 and Rn, where capital N is the number of samples collected. Okay, now that was the first step. What is the first step? We calculate the average, that is X bar, and range R for each sample. See, now here how many samples are there? N number of samples are there, capital N number of samples are there. For so many samples we have calculated. Okay, next, second step. Now calculate the grand average X double bar. See, actually this should be exactly on the letter X, but some problem I am facing with the PPT, that's it is slightly shifting. Okay, but it should be just above the letter X and above letter R. Okay, those bars. So now you have to calculate the grand average, or you can say average of averages, and the average range. Okay, that is R bar. These things you have to calculate. Now grand average means, now how will you calculate? X double bar will be summation of all X bars upon capital N, and range will be summation of all ranges upon N. Okay, where N is the number of samples or subgroups. Okay, so you calculate this. This is the second step. Once you have calculated the average of averages, that is X double bar, and the average of range, that is R bar. Now the third step is calculate the control limits. Now for control limits, now for in step 3 we will calculate the control limits for X chart. For X chart, control limit means there are two control limits. One is upper control limit and the other is lower control limit. Upper control limit we are calling UCL, and lower control limit we are calling LCL. Now UCL of X bar will be X double bar plus 3 sigma X bar, and lower control limit will be only that instead of plus we are using minus. X double bar minus 3 sigma X bar, where sigma and X bar are the standard deviation of averages. Standard deviation of averages. So that can be given by sigma that can be given by sigma prime upon square root upon of n. Okay, where n is the sample size and sigma prime is the standard deviation of the universe. Okay, and this can be given by r bar upon d2. Now r bar, we have calculated this is the average of range, but what is d2? Now d2 is a factor depending upon the sample size. This will be available in the standard tables. Okay, so now here you need not worry from I say what is this d2. You see, from the standard tables you have to choose this, and this depends upon the sample size. That means, if the sample size is 5, it may be something, if it's 10, something else like that. Okay, now the upper control limit and the lower control limit, that is UCL and LCL, can also be calculated by these formulae also. Okay, here you calculated using sigma. Now you can calculate using another coefficient like A2. If A2 means UCL will be x double bar plus A2 R bar, and lower control limit will be x double bar minus A2 R bar. Or it can be, you can use this coefficient A1 and sigma prime. In that case, this will be the formula, and here lower control limit will be the same but with minus, and it can be, you can be using coefficient A with sigma prime, then it can be like this. So any of these 4 formulae, see here, one formula, second, third, fourth formula you can use. Okay, so like that you have calculated the control limits for X bar chart. Okay, it is not X chart, X bar chart. Okay, now next, see, when you calculate, okay, I will come to this in a moment. Okay, now the fourth step is calculate the control limits for R chart. First, in the third step we have calculated for X bar chart. Now for R chart you have to calculate. You see, for R chart, upper control limit will be capital D for R bar, and lower control limit will be capital D3 into R bar. Now what are capital D4, capital D3? These things, see here it is written, the values of various factors like small d2, capital D4, capital D3, capital D2, capital D1, A1, A2 are based on normal distribution, and they can be obtained from standard tables for a particular sample size. You see, and here is one formula given for upper control limit and lower control limit. This is another formula. So for the range also, these for control limits 2 formulas are given. Okay, so now you have calculated control limits for X bar chart also, R chart also. Now you have to plot them. Now that is the 5th step. For plotting for X bar chart, the center line of X bar chart should be drawn as the solid horizontal line. You see, now I'll show you this. You see, this is X bar chart, it is mentioned here. This is R chart. Okay, this is for a quality characteristic which is strength. It can be strength, it can be like okay, yield point strength, you can say. Okay, so now on the x-axis we take subgroups in both cases, and on the y-axis we are taking mean for the X bar chart, and for R chart we are taking the range. Okay, and in the center now, this horizontal line, this is X double bar. You can see here X double bar. This is the horizontal thing we should draw first. Okay, you see, X double bar should be drawn as the solid horizontal line. and the upper and lower control limits should be drawn as dotted lines using the formula, the values that you have calculated in step 3. You see, now here, okay, here they didn't use dotted lines. Okay, if it is black and white, you can use dotted line to differentiate, but if you can make colored charts, you use some other color. Now here some purple color is used for lower control limit and upper control limit. Now these values, what you have seen, the X bar, you got it as 155.561. You see, so it is coming like this here, and our lower control limit is 154.262, so it will be plotted here, and upper control limit is 156.860, so it will be plotted here. So these 3 lines you first plot. The center one is X bar, X double bar, and the upper one is the UCL, and the lower one is LCL. These things you plot. Okay, after plotting this for the X bar chart, for R chart also you have to do similar thing. For R chart, solid horizontal line will be R bar, and the dotted lines are some other color like purple color in our case, are for upper control limit and lower control limit. Okay, now after drawing these 3 lines for both the charts, next what you have to do is, now X1 bar, X2 bar, X3 bar, so on are plotted in an X bar chart, whereas R1, R2, R3, so on, Rn are plotted for R chart. Okay, so now the first sample X bar is here, that is plotted. For the second sample, it is here. For the third sample, it's here. Fourth sample, it's here. See, you will get dots, and you can add with a straight line like this. So here, how many samples are there totally? How many samples? 20 samples are there. You see, this is 19 is for this is for 20. Okay, 20 samples are there. So for R chart also you will get 20. Okay, samples means subgroups. How many subgroups are there? 20 subgroups are there. Okay, and in each sample, suppose 5 are there, so 20 into 5, how many more totally items were checked? 100 items were checked. For after checking 100 items, we are getting these 2 plots. Okay, see, it is time consuming, tedious, isn't it? 100 samples if you check, you will get like this. Okay, now if any point is falling outside the control limits, they are indicated by cross, whereas points falling inside are by circles. Okay, you see here, because it is a colored thing, nothing has gone outside the control limits. Okay, I'll show you some charts where they fall outside and how they are showing. You see, in that case, here outside it is fallen, you can show red color. Okay, inside the control limits it is there, means it is blue color as it is shown here, you can use. Okay, next the sixth step is draw conclusions from the control charts. Once the control charts are drawn, you see, why did we plot this control chart? To draw some conclusions. By looking at that, we should be able to say whether our process is under control or not. Okay, so now lack of control will be when a point is falling outside the control limit. You see, above the upper control limit or below the lower control limit, if a point has fallen on either X chart or R chart, that means what? You see, the process is not in control. When all the points fall inside the control limits, then the process is in control. So the process is said to be out of control when a point falls outside the control limits, and it is out of control when a run of more than 8 when a run of more than 8 consecutive points fall on the same side, either above or below. Okay, so like that we should conclude whether the process is in control or it is out of control, or it is getting out of control. Okay, so sometimes this here is a note mentioned. If the LCL value is going to be negative, then you take it as 0. Okay, now objectives of Xbar chart and R chart. Now Xbar and R charts show centering of the process. Now you can see here that our figure we have seen, this is the center. Now all these values are falling in on either this side, that side, this side, that side only. You see, not so this is called centering. It's more towards the center. Okay, now Xbar R charts show any changes in the process average. If any process average is there, it will show. Okay, then Xbar R charts give the information about the appropriate action to be taken from changing the specifications and manufacturing process. So by looking at by studying that, you will come to know if any action is to be taken, any manufacturing process is to be changed, or the specifications are to be changed. That we can know. It gives the information. Okay, then Xbar R charts provide the necessary information to carry out process capability study. See, the process capability study, for that the information we are obtaining from Xbar R charts. Okay, next, the limitations. Now there are certain limitations. What are that? See, Xbar and R charts are impossible to be understood without training. See, you cannot understand. See, for that, no, you should understand so many things. You should be engineers. You should be mechanical engineers to understand this. It is not simple. Ordinary layman cannot understand. So this is a disadvantage. Okay, then Xbar R charts can cause confusion among tolerance limits and control limits. You see, now two things are there. When we are saying control limits, now what limits we have seen in Xbar chart and R chart, these are upper control limit and lower control limit. Here we call them as control limits, whereas another limits are also there, which are called tolerance limits. Tolerance limits means, when we are saying the diameter of the shaft should be 50 plus or minus 0.02 mm. So there the tolerance limits are specified by that tolerance. You see, that is 50.02 mm will be the upper tolerance limit, and the lower tolerance limit will be 49.98 mm. Okay, see, now sometimes there may be confusion, unless you give a good reading about this subject. Unless you understand properly, there will be confusion in your mind. Now there are two limits, which is this limit and which is that limit. Okay, so this is another disadvantage. Okay, now the third one is Xbar and R charts can be used only for one individual characteristic at a time. You see, for a diameter of there can be number of quality characteristics for an object, for a workpiece. Suppose there are 4 different types of quality characteristics. Suppose we want diameter also, and we want length also. Okay, like that, if you are having, for these two, we have to plot 2 different sets of control charts. So like that, for length 1, for diameter 1, for thickness 1, like that, so many charts you are making. Oh, see, it will be, you see, it is more cumbersome. Okay. Then the fourth one is Xbar and R charts are costly and time consuming activities such as measuring, computing, plotting. See, these are all costly. See, for 100 samples, we got these two diagrams. After making 100 measurements. Okay, see, like that, it is all costly and time consuming. Okay, but anyway, computers have made the life so simple, easy, but still measurements have to be taken. So the measurements, for man has to take, and the data things have to be entered into the computer, and all those things have to be done. See, they are time consuming, they are costly. So these are the limitations. Okay, now next, when we are studying about the X bar chart and R chart, what are the trends? You see, there can be extreme variation. Extreme variation means this type, this is a kind of error, you can say, or the you can say the process is going out of control. See, because of the extreme variation, process is going out of control, you can say, like. Okay, extreme variation. Sometimes no, even wrong pieces if we select also. It may be. It simply doesn't mean that the process is going out of control. Okay. Anyway, let us see what are the different trends in X bar and R charts. You see, extreme variation is recognized by the points falling outside the upper and lower control limits. You see, if any of the points falls on outside, then this is an extreme variation. Okay, the width of control limits on the control chart, that is the difference between upper control limit and the lower control limit, represents the variation due to the inherent characteristics of the process, which means the normal permissible variation in machines, materials, and men. So I'll show you one figure here. Yeah, you see here. You see the first chart here. This is because of the extreme variations. Now in this extreme variations, now this is the center line X bar, and this is the upper control limit and the lower control limit. Now here there is a point fallen outside, and there another point is fallen outside. A single point above or below the control limits can be treated as extreme variation. Okay, so you see, actually no, see you see, now for one object we are getting the dimension like this, for another we are getting the dimension. Okay, not one object, for one sample, you see. Okay, for one sample we are getting like this, for another sample we are getting like that. So why these variations are coming? Because there are variations, as we have seen in the previous lecture, because of the machines, because of the materials, and because of the men. All these 3M cube. Because of this, the variations are coming. But even if the variations are coming, these are the permissible variations, and they should fall within upper control limit and the lower control limit. Okay, now if any point has fallen outside, what are the causes? That means if extreme variation has come, what are the causes? The cause may be, you see, the measurement itself you have not taken properly, error in measurement or error in calculation. Okay, that is one. Well, that can be one reason. Second is samples chosen at peak position of temperature, pressure, and such other factors. See, that means you have to choose the samples randomly, but improper random sampling if you do. See, because of certain thing, where some high temperature has come into the thing, and at that time you are picking a sample. That means, because of that also the point can go outside the control limits. Then wrong setting of the machine, wrong setting of the tools can be one cause. Then samples being chosen at wrong times. Wrong times means samples being chosen at wrong times means either on the commencement at the beginning or the end of an operation, at that time if you are selecting. You see, you should not take, just when you started, okay, or just something, uh, after some break if you have started at that time, or like that, you should not take. You should take when there is, after so few pieces are machined, then you should take like that. Okay, so during production of the entire quantity over a long time, the intermediate products could not have any chances to be selected, to be selected for sample. Thus, the sampling does not represent the true picture of the entire quantity. See, if in the wrong time, if you are selecting, that means it won't represent the true picture of the manufacturing process. Okay. So you should, say, for that also you should take at the right time. By the experience you will know when to take and all. Okay. So this is the first extreme variation. Now there are three more here: erratic fluctuations, shift, and indication of trend. Let us see these things also. Second is shift. Shift means what? When a series of consecutive points fall above or below the center line on the Xbar chart or R chart, it can be assumed that the shift in the process has taken place, indicating presence of some assignable cause. Assignable cause means, because of because of the reason by, which we can trace. Assignable, chance cause and assignable cause. We studied about two causes. No, this is assignable cause. Maybe we induced because of the man who is operating, or maybe it is induced because of the machine, okay, or because of the raw material, see, like that, see. And it is generally assumed that when 8 consecutive points lie above or below the center point, the shift has occurred. Now let us see here. Now shift, this is the shift. In this shift, now see, now the process was going like this. Now suddenly 1 2 3 4 5 6 7 points, this is just on one side. See, it is not that the points are fallen outside the control limits. They are well within the control limit only, but still, no, see, some 7 points are in a line, one after the other consecutively, have fallen on one side of the mean value. See, even that, is indicating us something, some cause, some assignable cause is there, because of which this happened. What is the cause? What are the causes of shift? It can be change in material, it can be change in operator or inspector or inspection equipment, etc. It can be change in machine settings. It can be loose fixture if the fixture is not firmly fixed, okay, or it can be new operator or carelessness on the part of the operator. Okay, see, these may be the different causes why the shift is taking place. Now the third one is the erratic fluctuations. Erratic fluctuation means this may be due to a single cause or a group of causes which affect the process and the spread. Okay, the cause of erratic fluctuations is difficult to identify, and it may be due to different causes acting at different times on the process, like frequent adjustments of the machine, or different types of material being processed, or a change in operator, machine, test equipment, etc. See, erratic fluctuations means, how it is. You see, it is, like this. Some point suddenly is falling outside the control limit. Okay, and then on the other side it is fallen, then this side it is fallen. See, like such kind of fluctuations if it is giving, that is erratic fluctuations. Okay, and the fourth one is indication of a particular trend. Indication of particular trend means if the consecutive points on Xbar chart and R chart tend to move steadily towards one of the control limits, then it is indicating a trend. Let us see in the chart here. You see, now up to this point it was okay, but afterwards no, it is slowly moving towards. You see, it is not that the out of control limit it is gone, but still no, you see everything is going towards, after some point it may fall outside the control limit. See, the process is going out of control, you can say like that. You see, so this is called as the indication of trend. It means that change is taking place slowly, and even though at present all the points are falling within the control limits, but after some time there is a possibility that the process will go out of control. Therefore we have to take a corrective action. Why it is taking place? It could be because of the tool wear, or it can be wear in threads of clamping devices, or it can be because of the effect of temperature or the humidity, or it can be because of the accumulation of dirt, choke up, jamming of fixtures, holes, etc. These can be different causes because of the for the trend that we are seeing. Okay, now next topic become, that is the process capability. Now, like control chart, process capability study or method is also an important tool of statistical quality control. Okay, this is also an important tool. Okay, now first let us define what is process capability. Now, process capability is defined as the minimum spread of a specific measurement variation, which will include 99.73 measurements from the given process. You see, the minimum spread, where 99.73% means 3 sigma limits. 3 sigma limits. Okay, 99.73% measurements are falling within that spread. See, what is that minimum spread? That is called as process capability. Now, process capability, there is another definition. It can also be defined as the probability or rate at which product will be manufactured within the tolerance limits. Okay, so these are the two definitions. Okay, now in Xbar chart and R chart, we have seen that the variability in the process can be controlled within the control limits of plus or minus 3 sigma Xbar. Here 6 sigma prime is known as the process capability. 6 sigma prime. Okay, this is known as the process capability, restricting the spread of process within limits. So if we are saying process capability, it is 6 sigma prime. This is the natural tolerance. Okay, 6 sigma prime is taken as the measure of the spread of the process. Okay, see, by process capability study, it will be possible to know the percentage of products which will be produced within the plus or minus 3 sigma limits on either side of the mean X bar. So process capability means you can say that it is that spread of the variation in the measurements in which 99.73% measurements fall. Okay, so like that, this is the process capability. Now the importance or benefits of process capability. Now, process capability study is important because it gives detailed information on various aspects. It gives detailed information on various aspects which are mentioned below. 1. To find whether the process is capable of meeting the specified tolerance limits or not. See, now design engineer or design people, design department have given us the design specifications, which we are calling as the tolerance limits. Okay, so whether our process will be able to produce within those tolerance limits or not, our process capability will be able to tell us. Then second is to determine the centering of the process capability will be study is important. And then to find out the reason why the process is failing to meet the specifications, this also process capability will be able to tell us. Then the fourth one, to find out actual variability of the process. Then to improve equipment maintenance, operator training, reduce costs. It gives us indications. Then it helps to predict the extent to which the process will be able to hold tolerances. It helps to choose the appropriate process amongst the best competitive. So for comparing the processes also, the process capability study will be helpful. The chosen process should manufacture products which lie within the permissible limits. To decide the specification limits also, see, to decide what should be the tolerance limits also, process capability study gives you an idea. Okay, to test theories of causes of defects during quality improvement programs. See, suppose you have developed some theories of the cause of defects. For this reason the defect is coming, and you have some idea. See, that is your thought, so that is your theory. So to test those theory, this process capability will be helpful. To find out variation from piece to piece, from one piece to another piece, if variation you want to find out also, process capability will help. To reduce wastage during production, to save money as well as saving time, this process capability will be of use. Okay, next, now let us see the procedure for doing process capability study. Now first calculate the average x bar and range R for each sample. Calculate the grand average, that means x double bar, and the average range, that is R bar. Okay, it measures the centering of process. Now the third step is calculate the process capability. Now process capability is 6 sigma prime. Okay, that is 6 the sigma prime is the standard deviation, and it is calculated by this formula. Sigma prime is R bar upon D2. Now D2 is a factor which is available in the standard tables. Okay, now this measures the item wise variability of the process. Okay, which one? This one, process capability, 6 sigma prime. Okay, now step 4, calculate the specified tolerance, that is x maximum minus x minimum. This is this is the tolerance. This is from the design tolerance. It is not upper control limit and lower control limit. You see, that's what we were saying. 50 plus or minus 0.02 means 50.02 mm minus 49.98 mm. That means that is 0.04 mm. See, that is the tolerance. Okay, that one you can find out. Okay, and then x maximum, x minimum represent upper specification limit. The suffix SL and lower specification L suffix SL. See, this is SL, not CL. If it is USL means specification limit. UCL means upper control limit. Okay, there is a difference here. Don't confuse this and that. Okay, then step 5. Now compare the natural tolerance, this one 6 sigma prime, with the specified tolerance, this one. Now this you calculate from all the control charts what you got, that is the natural tolerance, and what is the design department has given us the tolerance thing, that is the specified tolerance. You compare this. By comparing these two, that is the natural tolerance, which is the process capability, this is not given by the design engineer. This is actually we are getting from the control charts. This is by actual measurements of a set of materials, machines and men. We are getting this. That is why it is called natural tolerance. That we are comparing with the specified tolerance, which is specified by the design department. Okay, then we will get any one situation out of the 3 situations described below. Now, what are those things? When we compare them, say first thing, one situation is, say this specified tolerance, that is x maximum minus x minimum, is greater than the natural tolerance 6 sigma prime. Okay, if it is like this, that means what? See here, x bar x maximum is there. This is the, like I was telling you about the shaft measurement, 50.02 mm. So x minimum is 49.98 mm. So these are the things. And now for different samples, what you have found out, our Xbar chart, R bar charts, they are falling within this specified tolerances. You see, that means what? It is good. Practically all the products manufactured will meet the specifications, whether it is coming here or here or here, it is all within this only. So anything will be meeting our specifications. If x maximum minus x minimum is very large as compared to 6 sigma prime, then it indicates that the process is much capable of producing parts within the permissible limits. Therefore, frequency of control charts may be reduced. You see, if everything is falling here or no, you need not be making so many calculations and measurements and other things. You can for less number of samples you can test like that. Okay, this is the first case. Second case, where the specified tolerance, that is x maximum minus x minimum, is less than the natural tolerance. Now natural tolerance, you see here in the figure, whether it is this case or this case or this case, in any case, some of the points are going outside the specified limits, design limits. Okay, so that means what? Here there will be defectives. Defectives will always be there. Okay, then suggestions. What you have to do? You have to talk to the design department. You have to increase the tolerance. Okay, use wider tolerances. But that may not be always possible. Second, reduce the dispersion. Find out the cause why this natural tolerance is falling outside the control over the specifications, specified tolerances. And if this machine is the problem, or man is the problem, material is the problem, try to correct it. Okay, then suffer and sort out the defectives. And if it is not economical to make any changes in the process, suppose if you are unable to make any change on the machines or the material or man, then what you have to do, you have to sit down and all those things which are falling outside the control limits, outside the specification limits, you have to throw them as scrap, but that may be too costly. Okay, this is the second case. Now third case, is where the specified tolerance and natural tolerance are exactly matching. They're equal. See, that means what? The spread of the process is approximately equal to the difference between the upper and lower specification limits. You see, exactly here and here, it's touching here and here. A little bit here, this side and that side, no, will bring some one or two pieces into defective category. That means this is also not desirable. See, among the three that we have seen, the first one is the desirable thing. Second one is not anyway desirable. Third one, no, is a boundary case. This is also not desirable. Okay. You see, suggestions. It is necessary to maintain the centering of the process. You see, now you have to be very careful. You see, because any mistake entering also may cause some of the parts to be defective. Okay. Then you can reduce the dispersion if it is economical to do so, and if it is feasible to do so. Whether this bell-shaped curve that you're getting, if you can make it, if you can compress it, you do it. Then it is advisable to increase the tolerance limits to take care against minor shift of centering of the process. If any from the centering any shift comes, it will fall outside. Therefore you think of taking little wider tolerance limits, that is x maximum minus x minimum, you increase. But if you are increasing like that, that means you are making a compromise with the quality. Okay, like that. Okay, see, okay students, we'll stop here for today. We will continue in the next lecture. Thank you.